All right, welcome back to linear algebra. In section 2.5, we're going to look at the problem of how we change coordinates in vector spaces. So in particular, in this first lecture of section 2.5, I want to show you how you can find the so-called change of coordinate matrix, converts coordinates of vectors in one basis into coordinates in another. That's theorem 2.22. And then I want to talk about the same idea, but converting the matrix of a transformation from one basis to another. That's theorem 2.23. Okay, let's just get going here. So if you have a finite dimensional vector space, I'll use this notation throughout this whole lecture. I've got two bases, beta and gamma, usual notation. So the dimension of V is n, beta basis vectors are called V's, gammas are called W's, they're ordered bases. And the basic question is, well, given some vector in the space, how do the coordinate vectors in those two bases compare? Or how are they related? Or maybe a slightly more precise question is, suppose I have the coordinate vectors of some vector v in the beta basis, how could I convert those coordinates to the gamma basis, right? So given the coordinates in the beta basis, how do I find the coordinates in the gamma basis? That's the question I want to try to answer. So here's how we're going to go for that here. Take any j between 1 and n. Let's look at the jth basis vector in the gamma basis and write it as a linear combination in the beta basis, right? So what am I saying? I'm saying let's find the beta coordinates of wj. I've called them q's, q1j, q2j, and so on, right? So those are the coordinates of wj in the beta basis. And certainly if I take the identity map on v, and I apply it to wj, I'm going to get wj back. So by definition, if I'm looking at the matrix of that identity map in the gamma beta basis, it's this matrix with these entries qij. So I'm going to call that matrix q. All right. Why is it by definition? Because remember, when you're writing down the matrix of a map in two ordered bases pairs, what do? You take each basis vector in the subscripted one down here. So each gamma element, that's a wj. I apply the map to it. Well, applying the map to wj gives wj back, and then I write that in terms of the upper subscript basis. So that's exactly what I've done. So you stack these coordinate vectors of the gamma basis you stack the coordinates of the gamma basis vectors in the beta basis into the columns of a matrix, and I'm calling that matrix Q. Okay, so some of our previous theory says that because the identity map is invertible, so is this matrix. That's theorem 2.18. A map is invertible if and only if its matrix in a basis pair is invertible. And moreover, an old theorem 2.14 says that if you take that matrix and you multiply it by the coordinates of a vector v in the gamma basis, you get the coordinates of the vector v in the beta basis. Okay, so this is sort of a mission accomplished. I'm just going to scroll down a little bit. What we've done is proved theorem 2.22. So theorem 2.22 says if you take two ordered bases for your vector space, and you let Q be the matrix of the identity map in the gamma to beta, that first of all, Q is invertible, we proved it, and second of all, if you left multiply Q by the coordinate vectors of a vector in the gamma basis, you're going to get the coordinates of the vector in the beta basis. That's true for every vector. Cool. Okay, so for that reason, we're going to call Q a change of coordinates matrix. And in particular, if you want to give the direction, left multiplying by Q changes coordinates from gamma to beta. Okay, so the recipe for Q was given. Left multiplying by it takes coordinates in the vector, takes a coordinate vector in the gamma basis and produces a coordinate vector in the beta basis. So we're going to say that it's the change of coordinate matrix from gamma to beta. All right. But you could certainly take this equation, Q is invertible, left multiply both sides by Q inverse. If I multiply by Q inverse on both sides, well, Q times Q inverse is 1, so I would exactly get this equation. If I take Q inverse times the coordinates of V in the beta basis, I get the coordinates of V in the gamma basis. So Q inverse changes coordinates exactly the other way, yeah? So I think that's important to think that Q, the way we've constructed it above, changes from gamma to beta coordinates. Its inverse changes back. So in my alternate question up there, I said, given given a vector in the beta basis, how do I produce its coordinates in the gamma basis? Well, I construct this matrix, take its inverse, which we'll talk about carefully in chapter 3, left multiply by it, and that does it. That converts my beta basis to my gamma basis. Nice. Let's look at an example. So I'm just trying to use the same notation as I did in the statement of the theorem. So I'm going to take my vector space to be the plane, R2. Beta is just the standard basis, but because I was using the letter beta in the statement of the theorem, I'm going to continue to use it. And gamma is this basis. I'm going to leave it to you to check that that's a linearly independent subset of the plane. So it spans, because there's two vectors in it, so it's a basis. Okay. So what's the recipe to make this matrix Q? Well, I have to take each one of these vectors. I didn't name them up here in the set. Sorry about that. This is my W1 and that's my W2. So the recipe is, okay, take W1 and write it in the beta basis. Well, W1 is 1E1 plus 1E2. And then I make those coefficients the columns of the matrix in the first column. Do the same thing for W2. W2 is minus E1 plus 1E2. So I put those numbers in the second column. There's my matrix Q. Okay. So just to illustrate, what does that matrix do? Remember, this matrix is going to convert. You remember the order? This matrix converts by left multiplication gamma coordinates to beta coordinates. So let's take some gamma coordinate vector. Let's say W is the vector 2W1 plus W2. Okay, so its coordinates in the gamma basis would be the coordinate vector 2, 1. And I might want to know, well, what is the coordinates of that vector in the standard basis? Okay, well, the coordinates of that vector in the standard basis I find by left multiplying Q by the coordinates in the W basis. So I take that matrix Q, I left multiply it by the coordinates of W in the gamma basis. You can check my matrix multiplication, I get 1, 3. Okay, so W in the standard basis is 1E1 plus 3E2. The standard basis is nice. You can write those coordinates like that. So it's 1, 3, and you should check. You should stop the video right now and check that this all worked, right? Because we wrote W is 2W1 plus W2. So you should check. If you take two W1s and you add a W2 to it, you're exactly going to get the vector 1, 3. So this process worked. In order to convert back, we need the inverse. Here, I'm going to borrow a fact right now. We'll justify this and talk about it in chapter 3. But if you want to invert a 2 by 2 matrix, you multiply by the reciprocal of this number AD minus BC. It's called the determinant. We'll talk about it later. And then you interchange the main diagonal entries in the matrix and negate the other diagonals. I'm not proving it here, but just take it as a fact. Okay, so if you have an invertible 2 by 2 matrix, that's a recipe for finding its inverse. So if you apply that recipe to our Q, you get this matrix. There's Q inverse, 1/2, 1/2, minus 1/2, 1/2. What does Q inverse do? It converts coordinates in the standard basis into coordinates in this gamma basis. Right, so let's look at an example. If we took, say, a V in the standard basis, take the vector 8, 2. 8E1 plus E2. So its coordinates in the standard basis is the coordinate vector 8, 2, or sorry, 8, 2 is a column vector. Then if I wanted to know, well, what are V's coordinates in the gamma basis? I left multiply by Q inverse. I'll let you check my matrix multiplication, but you get the vector 5, minus 3. Okay, and what is that 5, minus 3? That tells me that my V, this vector V, whose coordinates in the standard basis are 8, 2, if you want to write it in the gamma basis, you need to take 5 W1s and negative 3 W2s. Okay. I drew some pictures for you. Oh, here, I wrote that right here as well. So V is 5 W1 minus 3 W2. Here, I drew some pictures. This is kind of a busy picture, but let me kind of narrate it for you. So I think you can kind of see in red, I drew the standard basis, E1 and E2. I drew this picture to scale. So that's why some of my vectors are a little bit small there, okay? So there's my E1 and my E2, and then I've got my vector W. Remember when W was given in the W basis, where is it? W was 2W1 plus W2. Okay, so I'm trying to indicate that in the picture down here. This is the vector W that I'm looking at, in case you're not seeing it in my picture. There it is. And I'm kind of trying to indicate that that vector is two W1s. Yeah, I've got W1 labeled down there. It's two W1s, same direction, twice as long, plus one W2. Okay, so that's my vector W. Two W1s plus one W2. You can see W1 and W2's labels down there. And we converted that vector. So over here, I'm writing its coordinates in the gamma basis. Above, we computed its coordinates in the standard basis were 1, 3. And although you can't really see super well in the picture here without the grid, maybe I can turn the grid on. Let's see. If this is a disaster, I'm going to shut it back off. Yeah, no, you can see it kind of nicely. So now that I turn that grid on, you can see, sure, that W1 is also 1 E1 plus 3 E2s. Okay, so that's vector W's coordinates in the standard basis. It's 1 E1 plus 3 E2s. Nice. We also did the other way. I gave you a V in the standard basis. It was 8, 2. That's this V right there. You can see that it's 8, count them over, E1s plus 2 E2s. It's the vector V. By multiplying by Q inverse above, we found that its coordinates in the W basis was 5 minus 3. And I'm just trying to show you that. So here you can see that if you take 5 W1s, you can see it in the scale of the picture, right? W1 is kind of the diagonal of one square. So I'll just count them out. There's 1, 2, 3, 4, 5 W1s. And I add 1, 2, 3 W2s. Sorry, negative 3 W2s. So I go in the opposite direction. I get the vector V. So geometrically, that's what we were doing up there algebraically with those matrices. We were converting those coordinates. Cool. Okay, I hope you like that. Moving on here, that was the business about coordinates. What about linear transformations? Okay, well, let's suppose now that I've got one. Suppose that I've got some linear operator on a vector space. And let's recall the notation that if I write T sub beta, I mean the matrix of T in the basis pair beta beta, right? So if I write just one beta, then I mean that it's in both bases in the domain and codomain. And so kind of a mirror question, right? I just want to ask like, well, how are these two matrices related? The matrices of T in the beta and the gamma basis. Or if you like, a little bit more precise question, if I had the matrix in the beta basis, how could I convert it into the matrix in the gamma basis, right? So I'm trying to change coordinates from one basis to another. Okay, well, here's how we can proceed to do that. Let's take the same Q as we had above. Q is the matrix of the identity map from gamma to beta. And let's recall that when you compose the identity map with any other transformation, you don't change it, okay? So now I'm just going to make kind of a calculation. I'm just going to walk you through this left to right. I'm going to take that matrix Q and multiply it by the matrix of T in the gamma basis. But Q is the identity matrix in gamma beta. And then I just have the T putting in the gamma gamma notation. So stop the video and look this up. But Theorem 2.11 says that that matrix product is the matrix of the composition in the gamma basis pair, in the gamma beta pair, pardon me. All right, but we wrote above that the composition of 1V and T is the same as the composition of T and 1V, so I can just swap those. And then I'm going to use Theorem 2.11 again to pull those apart. That's the matrix of T in the beta basis times this Q. Okay, so if I put all of that together, if I sort of, I guess, right multiply by Q inverse on both sides, I get this equation. So that's kind of one answer to what I wanted to say, is that if you take the matrix of T with respect to the gamma basis, and you sandwich it in between Q and Q inverse like this, then you get the matrix of T with the beta basis. Multiplying by the inverse of Q and Q on the left and right, you can convert that into this equation. Okay, and that's really in the form that I asked. If I was given the matrix of T in the beta basis, how do I construct the matrix of T in the gamma basis? Well, I construct Q as above, and I multiply that matrix of T in the beta basis in this order: Q inverse T's matrix in the beta basis times Q. Okay, so this matrix Q, this change of coordinates matrix, it changes coordinates on the vector level, it changes coordinates on the matrix level. Nice. That's theorem 2.3, and that's where we're going to end. I'll just kind of walk you through it. If you're given an operator on a vector space, two ordered bases, beta and gamma, if you let Q be the change of basis, the change of coordinate matrix from gamma to beta, there's a direction here. So it's built into the notation. Q is the change of coordinates from gamma to beta, from new to old, I like to say it. Then the matrix for T in the gamma basis is this product. Oops, and that's a typo. This beta is supposed to be out here. Sorry about that. All right, so that's where we're going to end for day one. Thanks for listening.